All right, so this video is going to kind of walk through a couple of things that you were looking at. First one was that I heard that problem number one was going to be difficult, or that you're struggling with that one, so I thought I'd walk through that one first. And the second one was to talk a little bit about the car on the incline. So let's start with the problem number one, and it says an automobile is traveling along a straight road. It increases its speed from 37 feet per second to 54 feet per second in 180 feet. So again, as I go through this, I like to list out what I'm looking for. So I've got a V naught, an A, an X, and a T. My X naught is just going to be 0, so I'm going to set my frame of reference to be there. So I have a starting velocity of 37 feet per second. I have a final velocity of 54 feet per second, and this all happens in 180 feet, and they're looking for how much elapsed time is going to take place. So these are the variables that are given to me, and the A is not given to me, so the acceleration is not given to me. Now when I look at my relationships, I have this one plus AT, I have this, and I have this one. So these are the kinematic equations that are given to us, and we're going to use this to try to figure out which one we're going to do. Okay, and so if I look at my situation here, A shows up in all three of these equations. So no matter what I do, I'm going to have to find A first. So really, I'm going to put a question mark here, and I'm going to say find this first, and then I'm going to use this to find this second. So this is kind of my route that I'm looking for. So because I don't know time, but I need to know A, I'm going to pick a formula that doesn't have time in it. So this one has time in it, this one has time in it, and I'm going to use this one to kind of determine what the acceleration is. So I'm going to set this one up with my 54 squared equals my 37 squared plus 2 times A times 180. And so what I'm going to do is I'm going to solve this for A. So 54 squared minus 37 squared divided by 2 times 180 equals A. So now once you know what A is, then you can go back and you can actually plug that in to figure out what T is. And the easiest equation I think I'm going to use is actually this one right here, since I have my two velocities and I have my T, or my A, I'll be able to solve for that. So again, that's kind of the help to get you through problem number one. Let's talk now about the car on the incline. Okay, so the first thing that we wanted to address with the car on the incline data is that you should not have had any like total non-data points. So in other words, when I look at all of my data, these are all the numbers that came from my strip of paper, and I didn't end up with any zeros at the end because you should have had numbers that represented all your data, and you should only be graphing your data. So that was item number one. I know that in my video I just quickly showed a couple of points. I didn't extend all of the data that I had for that graph. So now this is one that actually shows all my graph. When we look at any of these graphs, there are some key things that we should always see. We should always see a title. Okay, we should always see the labels for the axes. So this is showing the displacement on this side measured in centimeters and time measured in seconds. So those are necessary items that you should have in any kind of a graph. Now when we look at the data points that we have, we can kind of see that there's a slight bit of a curve here and a curve here. So it looks like we're seeing two accelerations. And we're going to see that even better when we throw in that trend line. So here's how we go ahead and do a trend line for any data. I'm already in here, so I'm going to go to my edit chart. I'm going to go under customize down to series. Okay, and this is where I'm going to find my trend line. And that puts in that line of best fit. So you can definitely see that there's curves because you can see how the points are above here, below here, then they go back above here and they're trending back below. So there's definitely a couple of curves that are taking place. Now, to get the actual slope of that line, you need to actually do this, because there is an equation for this, and it's a linear function, so y equals mx plus b, but you have to actually use the equation under the labels to see that. So I'm going to throw that in there, and so now I can see this, and again, you can kind of adjust where you want your labels to be. I'm going to go ahead and see where I want my legend to be. I'm going to put mine at the top. There we go. Okay, so you can see that this is now showing the equation for that trend line. So the 57.3 is the slope, there's the x, and then the 14.7 negative, that's the intercept. So the reality is that this trend line is trending to show that I'm going to intercept down here. But the reality is the car started at 0. So my average speed was the 57.3. So that's how I get that average speed for my entire graph based upon that trend line. So that's going to give me that. Okay, so that's the item number 1. Now when we go into number 2, okay, I'm going to close this up. We're going to go into our velocity versus time graph. Again, we're looking to see if we can recognize the differences in our accelerations and where our maximum speeds are. So we started here at 0 velocity. We ended up trending in a linear fashion to this maximum point. So this would be my maximum speed right here, so 91.5 centimeters per second. And then we started to decelerate. So the trend again here is a line that goes this way. Now if I wanted to determine what one of my accelerations would be, I would look at the trend line of this data going this way. And then I would look at a different trend line for this data going this way. This is the downside of kind of using the spreadsheet, is it doesn't allow us to bracket our trend line. So in other words, if I throw in that trend line, let's go ahead and do that just to show what it looks like. Customize, we're going to go into series, go down to our trend line, and then we'll go ahead and put that equation in there. Okay. And we'll close that. Oh, let's make it so that our label is at the top. There we go. Okay, so if I look at this trend line is taking into account the acceleration going this way and the acceleration going this way. So this is really the average acceleration between two different accelerations. So that's what that slope would represent. So what I know is the slope of my acceleration down the ramp is going to be this direction. So it's got to be a steeper line, where this one was going to be my negative slope. So I would go ahead and I'd estimate this. Now when I go ahead and do my estimate, I'm going to kind of gauge based upon, let's see, high point here, low point there. So I'm going to kind of do a slope generalization between these 2 points. So like 91.5 and in 1.8. So I'm going to grab a calculator quick. Let's just do 91.5 divided by 1.8. So we're at about 50 centimeters per second. So that's our acceleration. So it's a greater slope than this would be, and that's how I kind of estimate that. Okay, I would do the same thing if I was trying to estimate the second acceleration, but I don't know if everybody had 2 accelerations. That's why there was a question about what was your acceleration. Okay, so that's kind of going over how I determine accelerations and maximum velocities. Now on a side note, if I wanted to, you can see that there would be area underneath this set of data, and that would represent the displacement that the car has traveled. So that was one of the things that we can get from a velocity versus time graph as well. Now when we look at our acceleration versus time graph, we're again looking for those 2 different acceleration points. And so what I'm doing is I'm trending a flat area here. This would be not the acceleration, okay, because we're looking for something to be about 50-ish based on what we just calculated our slope. So if I look at these data points, I've got 1, 2, 3 that are above the 50 line. I've got 1, 2, 3 that are below the 50 line. I've got these 3 are below, but then I've got 2 more that are above. So if I generally look at what I see, it's pretty darn close to that 50 mark up into this point right about here. So that's what I would say is my constant acceleration down the ramp. When we drop down, okay, this is dropping down and we're changing, so now we have our 0 acceleration, or our point where we had switched our acceleration, and now we have our negative acceleration. And so it would be a flat one down there too. So you can see that that acceleration actually was greater than the original positive acceleration. And you can see that back here because you can see that the slope here is smaller than the slope here. Okay, so the level of the slope is going to dictate what that acceleration is. Now, to kind of tie this into what we're currently learning about, which is free fall, we would expect that the reason why a car rolls down the ramp is because gravity is trying to pull it, but gravity would pull at 980 centimeters per second squared as its acceleration, and we're considerably lower than that, so we'd expect to be lower than that as we're going down that ramp. So that's why we're at that about 50 mark, is because we weren't using the whole ramp, we weren't straight dropping it, and we had a piece of paper that was dragging along with it. So if you would like to go back and fix your graph, you're allowed to go back and fix your graph, and if you wanted to go back and resubmit into the Google form on that, you can, and then you can resubmit that assignment, and I'll go ahead and credit you with more points if you so choose to do that. Hopefully that helps, and good luck with the next activity that does graphing.